Hello everyone, myself Purva Joshi. Today we are going to study a topic named curve tracing. So let's start with the first topic, that is monotonic functions. A function fx is called monotonic increasing if fx is continuous in the closed interval ab, fx is differentiable in the open interval ab, and f dash x is greater or equals to 0 throughout the interval ab. Okay, if these three condition holds, then we can say that a function fx is monotonic increasing. Okay, now here increasing function is shown. If f dash x is greater than 0, then the function is called strictly increasing. Okay, now a function fx is called monotonic decreasing if fx is continuous in the closed interval ab, fx is differentiable in the open interval ab, and f dash x is less or equals to 0 throughout the interval ab. Okay, so if this three condition holds true, then fx is called monotonic decreasing. Okay, here a decreasing function is shown. If f dash x is less than 0, then the function is called strictly decreasing, right? Now a function is called a monotonic in the interval ab if it is increasing or decreasing in this interval. Okay, now let's study critical point. A point C in the domain of a function fx is called critical point if either of the following are true. It is f dash of c is equals to 0 or f dash of c does not exist. Now let's study concavity and convexity. Now the function fx is called concave upward, okay, or we can say that it is a convex downward if again three condition, that is fx is continuous in the closed interval ab, fx is differentiable in the open interval ab, and f double dash x is greater than 0 throughout the interval ab. Okay, so this is a graph of a concave upward, or we can say convex downward, right? Now a function fx is called concave downward or convex upward if again three condition, that is fx is continuous in the closed interval ab, fx is differentiable in the open interval ab, and f double dash of x is less than 0 throughout the interval ab. So for concave downwards we have f double dash x less than 0. Okay, and for concave upward we have f double dash x greater than 0, right? Now this is the example of a concave downward or a convex upward, right? Now let's study point of inflection of a curve. A point at which f double dash of x is equal to 0 is called point of inflection, where the function changes the direction of concavity from downward to upward or vice versa. So as you can see here, this point P is a point of inflection. Okay, here it is upward and now this is downward, right? Now the next topic is maxima and minima. Now maxima and minima are the largest and smallest value respectively that a function takes either within a given neighborhood or on the entire function's domain. Now there are two tests. First derivative test for local extremum. Now what does this test says? Fx has a local maximum at this particular point if f dash of a is equal to 0 and f dash x changes sign from positive to negative at this particular point. Okay, f dash of a should be 0, okay, and the sign of f dash x changes from positive to negative. Now fx has a local minimum at x is equal to a if f dash of a is equal to 0 and f dash x changes sign from negative to positive at x is equal to a. Now second derivative test for local extremum. So fx has a local maximum at x is equal to a if f dash of a is equal to 0 and f double dash of a is less than 0. So for f double dash a less than 0 we have local maximum, and for local minimum f dash of a is equal to 0 and f double dash of a is greater than 0. Okay, so if f double dash a is greater than 0, then local minimum. For less than 0 we have local maximum, and the test fails if f dash of a is equal to 0 and f double dash of a is also equal to 0. Okay, so we can say that fx may have a local maximum or a local minimum or neither. Okay, now for solving the example we will use this second derivative test. Okay, now let's discuss one example. Discuss the function fx is equal to x raised to 4 minus 4x cubed with respect to increasing or decreasing nature, concavity, points of inflection and local maxima and minima. Okay. Now firstly fx is given. Okay, so we will find f dash of x, means its derivative. So derivative of x raised to 4 is 4x cubed, and from here we will get 12x square. You can take out 4x square common. Okay, so we have x minus 3 over here. Now we'll find f double dash x. Okay, so bring this 3 over here, so this is 12x square, and 2 over here, so minus 24x. Again take out 12x common from this, so you will get 12x into x minus 2. Now we will check increasing and decreasing nature. So firstly, fx is increasing function if f dash of x is greater than 0. Okay, now f dash x is what? 4x square into x minus 3 is greater than 0. So this is x square into x minus 3 greater than 0, right? So from this, what we can say that x minus 3 is greater than 0. Why? Because x square is always greater than 0. Okay, now so from this we can say that x greater than 3. So the function fx is increasing in the interval 3 to infinite, right? Because we have x greater than 3. So from 3 to infinite this function fx is increasing. Now fx is decreasing function if f dash of x is less than 0. Again write down f dash of x. Okay, so from this we can get x square into x minus 3 less than 0. Again x minus 3 is less than 0. We are considering this because x square is greater than 0. Okay, now from this we can get x less than 3. So fx is decreasing in the interval minus infinite to 3. Okay, now we will discuss concavity. Now fx is concave upward if f double dash of x is greater than 0. Okay. Now answer of f double dash x is what? 12x into x minus 2 greater than 0. So from this x into x minus 2 greater than 0. Now we want this. Okay. So there are two cases. If x is greater than 0, x minus 2 is greater than 0. Okay. Then only this whole quantity will be greater than 0. So from this we will get x greater than 0 and x greater than 2. Okay. So considering these two we can say that x is greater than 2. Okay. Now the second case is if x is also less than 0 and x minus 2 is less than 0. Okay. Both are less than 0. Then this whole quantity will be greater than 0. Right. So from this we can say that x is less than 0 and x is less than 2. Okay. So using this we can say that x is less than 0. Okay, so we have to write down the interval. So f double dash x is greater than 0 in which interval? From minus infinite to 0 and 2 to infinite, and the function fx is concave upward in this interval. Okay, now fx is concave downward if this condition hold, that is f double dash of x less than 0. Again write down f double dash of x. So from this we have x into x minus 2 less than 0. Okay. So now again we have two cases. Okay. So what is the case? If x is greater than 0 and x minus 2 less than 0. We want less than 0 over here. Okay. So either of the two should be less than 0. So first we are considering this case in which x is greater than 0 and x minus 2 is less than 0. So from this we will get x greater than 0 and x less than 2, means this interval 0 to 2. Okay. Now case 2. Now we are considering x less than 0 and x minus 2 greater than 0. Okay. So from this we will get x less than 0 and x greater than 2. Okay, but this is not possible. So we can say that f double dash x is less than 0 in the interval 0 to 2. Okay, and the function fx is concave downward in this interval. Alright, now point of inflection. Now at the point of inflection, f double dash x is 0. Okay, so f double dash x is what? 12x into x minus 2. So from this we will get the answer of x 0 or x is equal to 2. Now we will substitute x is equal to 0 in fx. Okay, so if you will substitute x is equal to 0 in fx, you will get answer 0. And at x is equal to 2, the answer of fx will be minus 60. Okay, so the point of inflections are what? From here we will get 0 and 0. Okay, and from here 2, and this is minus 16. So combination. So point of inflections are 0 0 and 2 minus 16. Okay, now we'll find the local maxima and minima. So at stationary point, f dash of x is equal to 0. Okay, so f dash of x is 4x square into x minus 3 is equal to 0. So from this we will get the value of x as x is equal to 0 or x is equal to 3. Now f double dash of 0 is 0. Okay, and f double dash of 3 is 36. Okay, so we can say that fx has local minimum at x is equal to 3, because here 36 is greater than 0. We have this condition that if f double dash of x is greater than 0, okay, then it is local minimum. So fx has the local minimum at x is equal to 3. Okay, so I hope you have understood throughout the session. Thank you for watching.